Broadcast is now starting. All attendees are in listen-only mode.
Eileen, let's get started. I think we have a good crowd and time to go ahead and get started with the webinar.
Great, thank you very much. And this is Eileen Sandher. I am with Onset in Applications. Thank you for joining us. Today, Dr. Laura Toran, the Weeks Chair in Environmental Geology at Temple University, is going to give her presentation of low-cost monitoring of stormwater control measures using water level loggers. Onset was founded in 1981. Laura has been using our HOBA water level loggers. We do have a global network of distributors. We are data loggers and monitoring equipment along with weather stations and water products. And everything is designed and manufactured in Bourne, Massachusetts on Cape Cod. The webinar is going to run for about 45 minutes. We will save 15 minutes to answer questions at the end. We may answer some questions as they come up if it seems pertinent to what Dr. Toran is addressing. And please do feel free to type your questions into the questions section of the control panel at any time. The webinar is being recorded and we will send a link to you in a follow-up email. And welcome, Dr. Laura Toran. Thank you very much. And it looks like we've got a little bit of detail. Laura, feel free to start on how you want to let everyone know part of the work you've been doing.
Okay. Yeah, they asked me to submit this bio, which just shows you that I'm a hydrologist. I work at Temple University, which is in Philadelphia, and I have a number of stormwater research projects in the area, and I'll be telling you about a few of them today. I use water level loggers and a variety of other loggers to do continuous monitoring to understand urban streams, look at stormwater control measures, which is the focus of today's talk, and I also do work in karst hydrology. Got a number of publications. I'll mention a couple of them to you today, and funding for the research comes from the National Science Foundation, EPA, PennDOT, and William Penn Foundation. I shortened the title here a little bit so that I could fit it on the screen. I'll give you a definition of green infrastructure in just a bit. But I wanted to start by saying that I really enjoy talking about monitoring. It's one of my favorite topics because there are so many interesting problems that you can look at, and it takes you to a variety of interesting places. This is a picture of me downloading a rain gauge on a rooftop. The photo on the right is a stormwater pipe. So there's stormwater pipes all over our neighborhoods, and when you're out there trying to monitor these things, you find out where they are. So to just give you a little bit of background on the theme of this particular talk, we're going to be talking about urban hydrology and the effect that impervious surfaces have on urban hydrology. This is a classic picture that shows up in a lot of papers and talks on urban hydrology, and it shows you the water balance, what happens to rainfall in natural systems and then varying degrees of impervious surface. And the point of this diagram is to show you how infiltration and runoff change as you increase your impervious cover. So runoff, the overland flow component, is increasing as you increase your impervious surface, and you build more buildings and more buildings. And when that overland runoff is increasing, your infiltration is decreasing, and that disrupts the hydrologic system. We're quite a bit different here in the natural setting than we are here in a highly pervious setting. But even just 10 or 20% pervious surface creates measurable differences that can affect our hydrologic cycle. The goal of green infrastructure is to try to increase infiltration. So we want to do something to put the system back a little bit closer to what it used to be. The reason why we want to do this is because all this overland flow and overland runoff causes trouble, causes habitat disruption. For one thing, this picture shows you a stream nearby, and when I take my students out to this stream, I tell them, don't be fooled by all the green here. You're not supposed to see tree roots in the air. That's a sign of erosion. You're actually not supposed to see a bank that's higher than the people standing in the stream. Again, that's a sign of erosion and down cutting. So even though there's a lot of green in this photo, it's an unhealthy stream. If you were living in that aquatic habitat, your home is getting disrupted all the time by storms. It's not a very friendly place to live right now. Another issue that comes up when you've got too much stormwater is sewer overflows. Some cities like Philadelphia have sections that the sewer water and the storm water end up in the same pipe. So about 60% of Philadelphia is in this situation. And it's better if these two systems are separate, so the storm water can go to a creek, but the sewer water goes directly to a wastewater treatment plant. What happens when you have a combined system is that the more stormwater you get, the less able this system is to handle it and divert it all to the wastewater treatment plant, and you end up with some overflow directly to the creek before it's been treated. And we would prefer that that not happen. So if we can do something to reduce our stormwater, we'll get less sewer overflows. So what is green infrastructure? I'm going to show you a couple of examples. There's quite a wide variety, but this will give you a pretty good flavor of it. You can have subsurface infiltration chambers. Basically, you have huge corrugated pipes with perforations in it that can store water, and then you surround them with gravel. So you're basically taking the subsurface and creating more storage zones there. And somehow you have to direct the water to these subsurface chambers. I'll show you some examples of that. Another really common green infrastructure are stormwater basins. They come in a variety of shapes and styles. And you see these a lot in neighborhoods. You get a lot of homes. The grass is essentially an impervious surface, and you need somewhere to put that stormwater, and you put a basin in neighborhoods. They don't always function properly, and that's one of the things I'm going to give you some examples of today. Sometimes we put plants in these basins and create wetlands, and that can create a good habitat for storing water and for species that like to live in this setting. A lot of people worry about mosquitoes when you start developing wetlands, but our experience has been if you throw a log in and you provide a lot of good cover for plants, for birds, they'll eat the mosquitoes, and these are pretty healthy environments. They won't cause trouble in your neighborhood. Porous pavement is one that people hear about a lot, varying degrees of how it's used. This is a photo during a pretty heavy rain event, and you can see the section where people are driving where it's not porous, the water is building up, but you don't see ponding here where the pavement is porous. It can be hard to keep that up, though. It can clog, and then it's not very useful anymore. So these are just a couple of examples of green infrastructure. What we're trying to do, as I said, with the green infrastructure is increase infiltration. And if you want to figure out whether green infrastructure is working, there's kind of two broad approaches you can use. You can construct a water budget where you figure out what all of these components are, and then you assess how your system is doing. What I'm going to be talking about today is a little bit different, and that is taking a look at just one component of this system. So doing a much more limited monitoring. You might see how infiltration is going, or you might just monitor runoff, but you focus just on one component. And that can reduce your costs for monitoring, as I'll show you today. What you need to do this type of monitoring are water level loggers. So typically 1 or 2 water level loggers to check different components of the system. You need an extra logger for barometric correction, and it's the same type of logger. It's an extra water level logger, but you leave it in the air to allow you to do a barometric correction. If you do not have a rain station nearby, then you need to get a rain gauge. a lot, you know, with weather underground, you can often find a nearby rain gauge that you can make use of. And then you need a shuttle to download your data. Both these pictures show somebody downloading data. So with a fairly minimal startup cost, you can set yourself up to monitor green infrastructure. And I thought I'd remind you of our funding agencies here, because the water level loggers that I've been using that I'll be talking about in this talk have been supported by NSF, EPA, William Penn Foundation, and then some local groups. Trout Unlimited bought a few for me, and the Warrington Environmental Action Board. So even kind of citizen scientists have got into the act here, at least in trying to get a couple of these loggers and have somebody monitor them for them. I think the key thing when you're trying to develop how you're going to monitor one component of this system is asking the right question. So you have to find a question that a water level logger can answer. One of them might be, are overflows or water levels, since we're using water level loggers, are they reduced after your green infrastructure is installed? Where is your overflow occurring? So you can maybe move the water level loggers around to find that out. How often does it occur? This is where the continuous monitoring is really nice, because it sits out there during the rain and catches one rain event after another, and you download the data and you can count it up. Sometimes we want to figure out whether storage is occurring. If you need to know how much storage, you're going to need a more extensive monitoring system, but you can tell by the recession on your water level logger that time after the storm whether water is being stored in a system. And then if you leave them out, you can see if the system changes after a while. So is maintenance needed to keep your green infrastructure functioning? You do want to pick your question carefully when you're doing this kind of monitoring. So I'm going to present 6 case studies today, and I will be able to get through them in 45 minutes. I'm going to give you just a little snippet from each one. It was hard to pick, but these are the ones I thought you might learn something from distinctly. And you'll see, I'll have them numbered so you can kind of see how the talk is going along. If you want to read more about some of these, I put a couple publications here where you can read in a little more depth, and I do have a couple more that I'm working on. Some of the studies today are in that first publication, but some of them, they were really small, and the only place you're going to hear about them is right here today. So this first case study is a wetland that was designed by Temple's Landscape Horticulture Department for the International Flower Show. So they set these things up in a convention center, and then when they finished, they decided to put it out on our suburban campus. And this was designed to capture roof runoff and put it into a wetland and store the water. And I wanted to see how well this was working once they actually put it in situ as opposed to inside a convention center. So I put one water level logger in the pond, and then I took a look at what was around this wetland, and I saw a little gully forming, and I thought maybe I should put another water level logger there and see if this wetland is overflowing, and if so, how often it's happening. So it's important to go out and take a look at your site and assess it, if possible, during a rain event. So let's dig in and look at some of the data. What I've plotted here is the water level recorded by these 2 sensors, one in the pool and one in that outlet. And then I've got the rain events plotted here so you can see how often it's raining. This happened to be a very, very wet summer, and pretty much every time the pool got water, we got overflow. This system was not functioning very well. So you can see the increase in water level here for both the red and the blue lines indicates that both of them are responding to storm events, and to very different sizes of storm events, every single one. So I monitored this for roughly a year, and I found that all of the large storm events overflowed the wetland, and about 70% of the events that were less than 1 centimeter, what I would call a small rain event, overflowed the wetland. And when it overflowed, it eventually moved out and crossed into the street on the other side of this field. So we were definitely not achieving our purpose of preventing flow on impervious surfaces here. I think a simple solution to this would be to raise the lip on the wetland on that one side. So let's take a look at a second case study. I mentioned in the beginning that quite a few basins fail, and this one was kind of doomed from the beginning. Before they did any retrofitting or repair of this basin, there was a concrete runway from the place where the water came into the basin directly to the place where the water went out of the basin. It's not much surprise that it wasn't storing water very well. I'm not sure who designed this, but the township recognized that this didn't make a lot of sense, and so they wrote a grant to retrofit or fix this basin. And their strategy was to dig down a little bit deeper and put a bunch of wetland loving plants in and get rid of that concrete flowway so that the water would actually have a chance to sit in the basin and maybe infiltrate a bit. Luckily, they did some planning ahead of time, and they let me know, well, at least a year in advance that they were going to do this. So I was able to put water level loggers out both at the inlet end and the outlet end a year before they did the reconstruction, and then I monitored afterwards. So I got it before and after. This was the before data, and what we see is that the water level response at the inlet was identical to the water level response at the outlet. I've got a similar plot to before where I've got two different water level loggers, and I'm plotting what the water level is, sorry about that, and how it responds to different storm events. And the timing was quite remarkable. I've zoomed in here so that you can see pretty much these are set at a 15-minute interval. So within 15 minutes, the water enters and then exits these basins. Let's take a look at what happened afterwards. Success. So we've got the same two loggers, and the inlet responds to storm events. But for these particular storm events, similar in size to the ones you saw on the previous slide, we did not get outflow. We did not see any outflow, so the basin was storing. Not 100% of the events, but you don't need that. You just need to get, most of the events and most of these small events being captured in the basin, and that's what's happening now. So that's good. So let's take a look at this third case study, and this is a parking lot on Temple's campus, and they decided to put some green infrastructure, an infiltration trench in this parking lot, and they put it in the median strip between the parking spaces. I'm not sure why, but they decided to put a traditional storm pipe under here too. Maybe they're kind of hedging their bets because this was one of the first stormwater control projects they put on campus, but it gave me a chance to compare a traditional storm pipe to one that has that perforated pipe and gravel right next to each other, receiving exactly the same storm events. So that's what I did. I compared side by side to see if the infiltration trench performed better. This is what the infiltration trench looks like. You saw a photograph of a huge set of these. This is just a single perforated pipe surrounded by gravel. It's 82 meters long, two and a half meters tall, roughly. And there were two inlets into both the traditional trench and this infiltration trench. So I put water level loggers in each of these inlets. And then I waited for the rain to happen and monitored for 1 or 2 years. Let's take a look at what happened in the pavement type. This is the traditional storm pipe. It's just set in pavement and takes water out to the street. And I've got rainfall in the dashed line on this scale. And then I've got water level in blue on the left scale. So again, you see storm responses. And man, every teeny tiny little rain event, we see it show up in that pavement pipe that has no gravel around it, the traditional system. In contrast, if you look at the trench that has the infiltration and the gravel and the storage, only the large rain events respond to storm. This is the same set of storm events, but you have to get a pretty big rain event before it you see it show up in the as a water level increase in the trench. So these little guys just don't record much rain, water level in that trench. So if we were to summarize what we see in all 4 of these inlets, the trenches have fewer storms, but they do tend to have a larger response. So once they stop infiltrating, they fill up with water. The pavement doesn't have quite as big a response, but every little storm goes right out to the street. There isn't any infiltration or storage going on. So we saw this through both of the inlets. I did notice a few exceptions. This is a storm where all of a sudden that pavement trench had a big response, and I wondered why. So I zoomed in on this particular storm event, and what we've got is that really big water level event, and then I plotted temperature on here too. Don't want to forget that these water level loggers record temperature, and sometimes there's some pretty interesting data there. And what I found interesting about this, these tick marks are at midnight. You know, that's when your day begins. I got a big temperature increase in this storm at midnight. You don't usually have warm storms in the middle of the night. They're usually a little bit colder. So I hypothesized that instead of the water going out to the street, maybe we were getting some backflow here, and some warm water that was stormed in the Philadelphia streets was coming up into our parking lot. So to test this, we went into the storm pipe and put a flow meter. That's not low-cost monitoring, but it's a way that you can follow up and answer some additional questions. And sure enough, we put that in there for a couple months, and periodically the flow direction reverses. So I wasn't even using it to quantify the flow. I just wanted to know the direction. And this is a case where we're actually storing water for the city of Philadelphia during a rain event, and that helps them out because they don't have quite as much water going down their sewer system if our Temple parking lot is storing it. And that's fine with us. It doesn't cause any trouble, but it's kind of an interesting thing. You might want to take credit for it if you discovered something like this. Okay. So what we saw in the parking lot was that the infiltration trench sees the infiltration trench infiltrates all the storms that are less than a centimeter. It only in big storms do we start seeing a water level rise, and that's pretty much how the green infrastructure is supposed to operate. Get those small storms off of the system. And then we observed backflow from the street pipes, which we uncovered due to a temperature increase during a nighttime storm. So let's go just a little bit off campus and take a look at a blue roof. Blue roof is a green roof without plants. So let me show you what that means by using these pictures. This is an apartment complex right next to Temple, and it has a series of wings, or what they call bars, that are 2 stories and 4 stories. And on the 2-story wings, they put a green roof, because the people in these apartments can see the nice green. Mostly sedum in here, and this allows them to have some roof storage. On top of these taller wings or bars, they put a blue roof. So they didn't bother with the plants, but they do have a lip on this, and it allows storage of water. They have ventilation pipes on this roof, but they also have overflow pipes, so they won't start storing so much water that the roof could have too much weight and collapse. So they have that built into the design. I'll show you some close-ups of these overflow pipes pretty soon. So this complex is known as Paseo Verde, and it's the first LEED certified low-income complex in the U.S. It's a pretty interesting place to do a little bit of green infrastructure monitoring. So guess what I did? I put water level loggers on these roofs. I picked 2 of them and put the water level logger on. As I said, they call these bars. So I put one on bar 1 and I put one on bar 3. And again, I monitored for actually a couple of years. And the thing that I noticed pretty quickly was that as soon as the rain stopped, the water level dropped. So, you know, this rain event lasted probably probably about 6 hours. I've got tick marks every 12 hours on this plot. And when the rain stopped, boom, the water level went down right away. So there isn't a lot of storage going on this roof right now. It seems to drain immediately after the rain stops. And that goes down into a storage system beneath and then out to the city streets. So this is less than optimal. And we wondered if there was something we could do to create a little bit more storage. So what we did, this is a close-up of this overflow pipe. We put a little piece of plastic and we just wire tied it on, and we cut the hole in half. There's actually 2 holes in this overflow pipe. Actually, there's a third one when you consider the one at the top. But this first one gets the first bit of storage. This one gets the storage when things are getting really hefty with the rain. And that one at the very top is when panic has set in and we're getting a heck of a lot of overflow. So all we did is cut that overflow pipe in half. And it cost us about $5 per drain. There were 5 drains on the thing, $25 solution. I'd go low cost for my remediation too. So you remember I was monitoring 2 different bars. I only fixed one of them. So blue is the one that I modified. And we saw this was the first rain event after we put this in. We saw right away that we had extended the storage time. So you see what I was shooting for is that I wanted to have the water level stay on the roof sometime past the rain event. We got about 3 extra hours here of storage, and that's going to reduce pressure on the storm pipes below. So that's good. However, it created a new problem. When the water was being stored on the roof, it slowly built up sediment around these drains, quite a bit of sediment. It did not happen right away. The first couple times we went out, we didn't see it. It took about 6 months, and actually kind of suddenly we started seeing sediment building up around these drains. And it actually creates ponding, where the storage is actually quite a bit longer, barely detectable by a water level logger here, but the water is staying on this roof well past the rain event, because sometimes with this mud, we actually clogged our little overflow hole completely. So one of the things that this illustrates is that if you just monitor for a short period, you may not see all the functioning of your system. It's a good idea to monitor, preferably for about a year, minimal a year, I should say. And that can check the potential for roof overflow because of this clogging here. It's kind of amazing how much dirt there is in the city when you think about it. We didn't see this. This is the drain without the reduction in the drain size, and this is that same one with the reduction in drain size, but same dirt's falling both places. It's just we got an opportunity to see it on this one. And they're going to have to decide whether they want to add these, the owners of the building are going to have to decide whether they want to add these reductions to all of their drains and then have somebody go up and maintain the roof, or not bother. From what my initial discussions with them, I think they're going to go ahead and put the restriction on and just have somebody come up and empty the dirt off every once in a while. This was probably 7 or 8 months in. Okay, so bear with me. We're heading into example 5 now. I mentioned to you that these roofs drain into storage chambers below. So we're going to take a look at one of the storage chambers below a roof. Temple put in a new science building called CERC a couple of years ago. And when they were designing it, they captured the roof water and put it into an infiltration chamber next to the building. Bunch of perforated pipes surrounded with high permeability material. And when I heard about their design, I said, why don't you put some wells in and we'll see, we'll take a look at what infiltration is going on beneath this basin. Not a common thing to do to put wells in around a basin, but I thought this is a science building. We should take a little closer look. So I went to a lot of construction meetings, and finally they did agree to do it. And one of the reasons is that monitoring green infrastructure helped them get points on their LEED certification for this new building. So monitoring can help you out with LEED certification. That's where LEED certification is where you've identified that you're a low impact building, and there's different levels of LEED certification. So I got 3 wells put in this basin to monitor infiltration beneath this chamber that was receiving water off the roof of this building. What the water does is it collects on the roof, and then they put it into a cistern. They use some of the cistern water in the building for gray water, and overflow of the cistern goes into this infiltration basin with corrugated pipes. So they put the wells in during construction because they didn't want to poke holes in the basin once they fit it. And you can see 2 of the wells in this shot here. They painted them pink to try to keep from running over the wells while they were finishing construction, but that failed. They ran over at least 2 of them because I saw them all bent over and crooked. And I actually lost one of my water level loggers because when they shoved the well back in place, they shoved it on top of it. So I have an Onset logger at the bottom of this well that you see here, and I'll never be able to get it out unless I remove the well and dig another hole. But I just put another water level logger in there when they finished construction. So this is what it looked like when they finished. The wells have been cut off, and you can't even see they're there. It's pretty much just me and my students that know they're there. And we download it once a month, the data once a month. And that's the new science building in the background. So let's take a look at what we were trying to figure out by putting these wells in. This is a schematic here of the infiltration trench, of the infiltration chamber receiving the roof water. So some of the water might come in directly from rainfall on that basin, but most of the water is going to come in from that rooftop. And what we want to see is when that water comes in, does it raise the water level up and start getting into these storage pipes? They recommend that you keep the water level at least half a meter below your infiltration chamber. That's considered best practice. So we want to see through these wells whether this is rising up too high. This is a pretty big concern when you try to put green infrastructure in a city, because people who live in the city don't want their basements flooded. So they want to know, are you raising the water table here? And there have been some small scale models to suggest that it's fairly minimal, but you really need to look at it on a case-by-case basis. So I've got my 3 wells, and I've got my water level loggers in them, and I've got the water level plotted here for the 3 wells in 3 different colors, and then I've got my rain events recorded. And what we found, we put that line that we're not supposed to cross here on the water level plot. We found one of the wells pretty regularly crosses that line. It's not doing it egregiously, but it is getting up into the very bottom of the chamber. In our case, with this particular building, they have scientific equipment in the basement, and they have very, very good sump pumps. So we're not too worried about the basement flooding. They've got it taken care of, and we aren't quite at the flooding level, but it does indicate that it's something that'd be a good idea to keep your eye on. One of the things that I mentioned is that we know that most of the water is coming in from the cistern and relatively little from direct infiltration. Start to get a little quantitative here, not just telling you whether the water level went up. We were able to figure this out pretty carefully because we put a sprinkler on the basin and created an artificial rain event, and we saw no water level rise in the wells. We could see it in the soil moisture, but it didn't penetrate the wells. So we created a 1.5 inch rain and just flat water levels in these wells. So we know this arrow is a lot bigger than this one. So we're on our last case study here. This is the most complicated one that I'm going to show you, and I'm going to give you an example of some more quantitative analysis that you can do with long-term data. Krabby Creek, which is shown in this digital elevation map, is an urban stream west of the city, not very far from Valley Forge National Park. It's one of the fastest growing areas in the metropolitan region. And all the development has led to some undercutting in this stream, very incised banks. Parts of the stream are starting to get in close to some of the storm sewer systems. So the people living there wanted to do something about this so that their living near the stream didn't cause so much undercutting. The stream is flowing to the north here, and the people in these neighborhoods agreed to a rain barrel and rain garden program. They let me know ahead of time, so I was able to put a water level logger out here before these retrofits or these green infrastructures went in. So they put in 15 rain barrels for rain gardens, and then the township put in 3 infiltration trenches. So on the side of the road, they put some stormwater chambers. Here's a photo of my data monitoring point. I put it in a railroad bridge so that when the water level went up, when the storms came through, the water level would go straight up, and I'd be more able to compare before and after because it wouldn't be overflowing on the side of the streams. But a restricted area kind of gives you a little better idea of consistency from one storm to the next due to your water level. One of the questions that we got ahead of time from the webinar was, how do you secure these water level loggers? I thought I'd address that on this site because I actually did lose my water level logger here. I haven't lost very many of them, but I pounded this one in. I pounded a 3 to 4 foot stake in and attached. That was not easy to do. I had some help. I attached the water level logger to that, but some massive storm came through and disrupted the sediment inside this bridge and washed out the stake. It undug it from that 3 feet down, and it washed away. I don't know how big the storm was because I lost my water level logger. So when I put it back in, I attached it to a tree, and I'll show you how I did that. What I do is I get wire rope, and I get these clamps. I have a pretty heavy investment in Home Depot clamps, and I tie it off to a tree somewhere. So this serves 2 purposes. If the water level logger gets blown away by a storm, it will remain attached to this wire rope. The second thing is it's pretty hard to steal these things. The rope is fairly difficult to cut. You have to have some pretty stiff shears to get that cut. And these clamps take a 7mm wrench. They will not work with an 8mm wrench or a 6mm wrench. And so unless you just happen to be carrying around a 7mm wrench, you're not going to be able to take them out. So it discourages people from stealing them as well. What I did in this case is I strung the wire all the way to the side and then along the side until I could come out of the railroad bridge and find a tree to attach to. One of the reasons you do that is all sorts of things, leaves and rags like you see here, come flowing down these streams. And if you leave this wire up in the air, it's going to create a tug on your water level logger, and that's not good. So other than this one, which I didn't have wired down, I can only think of one other that I lost. It was out for about 7 years, and I don't know if the wire finally wore through by rubbing against the stilling well, or if it got stolen. I really couldn't tell. But that's a pretty good record. Let's look at our data. You've gotten used to these plots now. We've got water level response, and we've got rainfall. I began monitoring in 2009, and then they put the control structures in 2011, and I monitored for another year, year and a half. That's a lot of data. And one of the things that you want to look at is how it's responding to different size storms. And you can't just stare at this data and figure it out. You need to do something a little bit more quantitative. So I chose to do time series analysis. it's a pretty simple concept. If you've got rainfall, your water level response occurs sometime afterward. And the time afterward is its lag. Also, a given size rain event will result in a certain height of response in your water level, and that's your correlation between the two. So this equation provides you with both. It shows the difference between the mean for both the first signal and the second, and divided by the standard deviation, and this gives you your correlation. The math is fairly straightforward, but best of all is there's MATLAB scripts for this. So if you feed your data into MATLAB and you say, give me the lag and give me the correlation, MATLAB will do it for you. What we're looking for, the question that I was trying to ask here was, is there a change in my time series before and after the GI? If this lag increased, that would indicate more infiltration took place. And a lower correlation would indicate less volume. So again, my questions are somewhat simple. I'm just using a little more sophisticated analysis this time. And I popped in a year at a time and one season at a time, and I could not find any difference before and after the green infrastructure. So I think it wasn't too surprising because their program only included a relatively small area being impacted by their green infrastructure. I think they were hoping for a little bit more. Doesn't mean you shouldn't do these kind of things, but you got to start somewhere, and you don't want to overpromise what just a few rain barrels will deliver to an urban stream. I would like to point out not all monitoring is low cost. This is a site that I've got 47 loggers, and there are a variety of different types. I have turbidity, dissolved oxygen, water level, light, conductivity. Not all problems can be solved with this. This is a stream where we're trying to evaluate an appropriate TMDL, and I think you need more intense logging for a question like that. Let's look at our tips. You've got to visit your sites regularly. These loggers can get blown out. You can see my little wire here now that you know to look for it. When the storm comes blasting through here, the logger may not stay in place. You got to visit regularly and put it back. And you need to look at your data regularly. If I hadn't been looking at my data, I wouldn't have spotted that water level increase or the temperature increase and found another interesting question. Monitor long term. If we hadn't left the logger out after we saw that the storage worked on that blue roof, we wouldn't have known that the sediment built up. And if you don't get long-term data sets, it's harder to do that quantitative analysis. So don't be too impatient to answer your question. I don't know if any of you are XKCD fans out there, but a lot of the people in my lab like reading this cartoon. This guy has kind of a quirky humor and pokes fun at science. In this cartoon, he's got an evil lord saying, we're going to have drones take control of the cities and we'll detonate the devices and California will break off from the mainland and drift out to sea. And his minion says, oh, how far out to sea? Will it put any of the cities in the UTC -9 time zone? What? I don't know. One request, can we make sure this doesn't happen during daylight savings changeover? And the caption says, you can tell when someone's been, and he said programmer, but I said data logger user for a while because they develop a deep-seated fear of time zone problems. You do have to watch out for time zones. Your logger isn't going to automatically change when daylight savings comes on. And if you set your logger with a computer clock that's been changing automatically, you can have a time zone, a time change shift when you aren't expecting it. It's not going to be 2 a.m. in the morning when you go out and download your data. What I recommend, always take field notes about your download time so that if you forget, you can go back and figure out what time the logger should have been reading. I recommend you pick a time zone and stick with it. I keep all my loggers on Eastern Standard Time. We don't do daylight savings. And pay attention to your computer when you're communicating with the shuttle and the loggers. So a little bit of humor here, but it is a serious problem. We've spent a lot of time correcting mistakes sometimes when we didn't pay enough attention. So we're 1 minute away from wrap up. I told you I'd finish all 6 cases in 45 minutes. water level loggers can be pretty helpful for answering targeted questions about stormwater. These are some of the questions that I showed you examples of, looking at how performance is after GI is installed, looking at where and how often stormwater overflow occurs, using that response after the rain event to look at recession and evaluate storage, not quantitatively, but just whether it's occurring, looking to see if maintenance is needed, such as the sediment buildup and what the long-term performance is. Once you've done this, you can often develop a question that needs more expensive monitoring as follow-up and modeling, and that could be a big help in answering additional questions. So I thank you and welcome any questions at this point.
Laura, it does look like, this is Eileen, you did address that you exported some of the data from overflow to use MATLAB.
Yeah, I pretty much store all of my data in Excel files. People have different software that they like to use, and you can talk directly between Excel and MATLAB. Usually there's a little bit of formatting involved, and you have to watch out for the data lining up. MATLAB is unforgiving of gaps in data, so you've got to make sure you don't have any gaps.
We had a couple other questions. I know on, we do have some tech notes available on our website, and we can certainly address any other questions that come up of a more technical nature.
Yeah, I see one here about using them in outside of the water, and that's a good one to answer, to address. If you notice this storm pipe here, it dries up in between, and I've seen no damage to the logger from that. And that makes sense because we use these for our barrow pressure too. So in this situation, when you subtract your barrow, which in my case, my barrow logger was right above this one, when you subtract your barrow from a dry pipe, you get no water level. But I know when I first put it out in a dry pipe, just waiting for the storm to come, I kind of wondered if that was okay. I've gotten very good data. It looks fine. And it doesn't seem to cause any damage to the logger. It doesn't wear it out in some sense. When I'm in a very fast flowing stream, I do use stilling wells, a little pipe around it, to make sure that the water isn't hitting the transducer directly. Sometimes that can create noise. If you see noise in the data, that's what that is. So I'm looking, yeah, so somebody noticed the stilling wells that I've used sometimes in that basin example. There's some, I think I used them in this basin just because I didn't have anything to attach to, and I was able to get those in there. But most of the time when I'm using a stilling well, like in the parking lot, I didn't worry about it. The water wasn't flowing through that fast. If you just start seeing a lot of noise in your data, sometimes what I'll do is just look at it first and see, well, how does it look? This is fairly smooth. And since I'm trying to compare one water level to another, I'm not too worried about the noise down here. I want to see how the rain peaks compare. That's close enough to answer my question. So I didn't have any stilling well in that case. I didn't have any stilling well in here because I couldn't, they were underground. I just got them to let me tie off to the inlet pipe. I was just tying off the logger to the grating here. They didn't let me down inside there. And that's, the water level data looked pretty smooth to me. So sometimes I'll put it out and see what it looks like and then decide whether to use a stilling well.
Laura, we sometimes get asked some easy ways to mount them too. And typically I might suggest slotted PVC, but I am relinquishing those suggestions to you today. Yeah,
you do have to slot the PVC if you put it inside there. You want to let the water in. And it's really just to keep fast flowing water from hitting that transducer. And I do it on a case-by-case basis. For these, for the grate, I just strung it from here because I couldn't get down inside. For the storm pipe, I put a garden stake in here and propped it in. Sometimes I have a cross stake to get it a little bit more stability. If I can get any kind of a bed to hammer into, I'll use a stake. As I said, I hammered that in pretty deep, but I still needed to attach it to something. So I use both rebar and sometimes stakes. There's garden stakes with holes in them that you can thread your wire rope through. Like I said, I've only lost one in the years that I've been working, so that's pretty good.
Laura, we had one question I see that they were asking about Bluetooth units, and I can answer that.
Yeah.
Seems like most of what you are using are our standard, either the stainless or the polypropylene that you connect with the shuttle to download
Yes.
to Overflow Pro, and then you were exporting data. We do have another kind of logger that does use Bluetooth with a direct read cable for some certain groundwater wells where the barometric pressure is at the top and in air, and the logger transducer is in your water. So we do have a couple other technologies. If that's appropriate, people can certainly contact us and we can follow up with some of those individual questions as well.
I know some of the people wrote in earlier asking about stage discharge curves. And that is something that we're doing on that Wissahickon project I mentioned, where we're doing higher level monitoring. What we do there is we leave the water level logger out all the time, and then we have to go out during rain events to measure flow. And measuring flow is quite time consuming and requires more expensive equipment. But once you do that, those water level loggers tell you what's happening for many more storms. So if you can develop the curve, you've got quite a data set. I think the most frustrating thing is that it tends to rain at night. I don't know why that is, but you can't really go out very easily at night and measure discharge. So, but once you get that, it doesn't matter when it rains, and then you've got lovely data day and night. One of the things I recommend if you do try developing a stage discharge curve is to take a few hand level measurements in case your water level logger gets disrupted, kind of as a backup. One person wrote in about asking about how to do the green roof monitoring. As I said, I actually was doing a blue roof. We didn't see a terrific place to monitor on this green roof where water was sort of concentrating. What we did on the blue roof was just put a little pipe and a piece of rock nearby and have it near the overflow pipe. And that was a low point on the roof, so we knew the water was piling up there. And that allowed us to keep the water level logger vertical. I think it's possible to use them both vertical and horizontal mode, but I don't know that I would want to switch in between. Once you get it set up, try to keep it the way it was.
Laura, I can add a little bit to the green roof question. We do have several different methods that are being used, and sometimes if it's an area where they don't want to visit the site as often and they want to get internet access, we do have some solutions for that as well, with adding water level, rainfall to an internet-based data logger. And we can handle more details after the webinar as well, any questions we didn't get to.
Yeah, I could see where that would be convenient. We have to get somebody to let us up on this roof every time, and sometimes it's the maintenance guy for the building, and he's very jolly about it, but sometimes he's busy and we wait around until he's free to let us up. They have high bars or railings around this roof because they are doing quite a few things on there, so it's quite safe once we get up there, but they do keep it locked. So there'd be quite an advantage to Bluetooth in that kind of situation. Somebody asked how high suspended solids can affect the measurements. For water level, I haven't seen an effect. And I'm monitoring some fairly turbid streams. And I can't say that I've actually done a lab study, but I haven't seen something that looks obviously like disruption. I don't know about conductivity loggers, but I think for the water level logger, one thing I did do in the lab was I had a water level logger get buried, and I wondered if it was still measuring the water level above it or not, and it does. So I put a bucket of sand filled with water and then put water on top, and I buried the water level logger, and it did accurately measure the water level. So I don't think sediment affects the transducers.
We do get those questions. Our tech support team probably handles most of those. I do know that it doesn't damage the logger. It can simply be washed out. It might clog the ceramic pressure transducer a bit, but I think it's able to be worked out in the software, and it wouldn't damage the data logger.
Yeah, like I said, I've had some pretty turbid, had these in some pretty turbid streams, and they function. They seem to function fine. Okay, we're getting pretty close to the end. I know, Eileen, you wanted to go through a few other resources for the listeners.
We will. We do have quite a few learning resources from Onset, and some training videos, some nice short detailed trainings on specifics. We do have a knowledge base, and all of those are coming up on the website. I do want to point out we did have a few questions here that we didn't have a chance to get to in detail, and I or someone else here in the sales and applications from Onset will make sure we address those individually. We'll contact you, answer your questions in writing, or give you a call, and make sure you have our contact information. So we'll be able to address any of those questions we didn't get to. Laura, thank you so much. We have your contact information. I know you said you'd be available for certain times and questions. I'm available 8 to 5 Eastern Time. Technical support is available 8 to 8, Monday through Friday Eastern Time, and we're happy to work with any of you on any specific application questions. All right, thank you so much for presenting this. Everyone, thank you for attending, and we will follow up with you after the webinar. I'm sure you'll be hearing from us next week. Thank you so much.